Hi, and welcome back. So, today we're going to continue with the scale of the universe and how we got to measure things the way we discovered them. So, in the last episode, we left off with the Earth uh, position in the solar system, the distance from the sun being determined from the uh, transit of Venus. And the Earth's diameter was measured to be 186,000 miles, 186 million miles. It's 93 million miles from the sun on average. So once you have that, you can use that and the same technique to measure the distance to Venus to measure distances to the nearby stars, up to, I believe, a couple of hundred light years. So, given that, astronomers began measuring distances to the local stellar neighborhood. And some of the stars that they measured were Cepheid variables. Uh, it's a variable star. Its name is derived from Delta Cephei, one of the first variables to be discovered in this class, thus its name. In the Cepheus constellation, other stars that you might know is Polaris is a Cepheid variable. And one of the brightest Cepheid variables is RS Puppis. Why are we bringing up Cepheid variables? Well, this is where the story gets interesting. You see, back in the early 1900s, there were female astronomers in Harvard University. The men did the observations and the women did the calculations. And one of these women was Henriett, Henrietta Swan Leavitt. Okay, this is important. She began measuring Cepheid variables, or what were believed to be Cepheid variables, in large and small Magellanic Clouds. I believe it was mostly the large Magellanic Cloud, but I think she did measurements on the small Magellanic Clouds. And what she discovered is, and here's the trick, she assumed that the stars in the large and the small Magellanic Cloud, because they're in a group, were approximately the same distance to the Earth. So she can take out an unknown variable, meaning distance. So any observations she made could be used and not have to worry about distances. It's a little convoluted. So Henrietta Swan Leavitt made observations of the small and large Magellanic Cloud. And one of the observations she made was that the period of Cepheid variables in the large and the small Magellanic Cloud had a linear relationship when using a log scale believed for parent brightness, that there was a linear relationship between the brightness and its period, between when it's peaked and when it's dim. Okay? And with this, she was able to determine that the large Magellanic Clouds were an X unit further away than her reference star. I believe it was Delta Cephei. I think she determined that the large Magellanic Cloud was 100 times farther than Delta Cephei. If it's wrong, I'll put a correction in the video. So, how is this important? she was able to now utilize a standard candle, as it's called, to distances to distant stellar objects. It's very hard to know how bright something really is if you don't know how far away it is. But it's really easy to measure how fast something goes dim and dark, dim and dark. Sorry. Light and dark, light and dark. Okay, these are all unscripted. Please forgive me. These videos will get better hopefully with time. But the big takeaway is she published this and they now have a standard candle to the outer universe, right? So we went from knowing the ratios of the solar orbits of all the planets, using parallax and the transit of Venus to determine the distance of Venus. And then from determining the distance to Venus, you can determine the distance to the sun, right? Because you know that your distance to Venus is a small fraction. I think it's Earth to Venus was 23% of the total distance to the sun. So if you know 23% of the way to the sun, it's really easy to get 100% the way to the sun. So we go from there. We go from knowing the size of the Earth's orbit to using parallax to knowing distances to stars. Some of those stars were Cepheid variables. Those Cepheid variables then gave us a distance marker to the small and large Magellanic Clouds, right? Because you can assume all the stars in the Large Magellanic Cloud are the same distance to the Earth. So you can develop that relationship. What made the Cepheid variables so special, so important? Well, it comes down to that they operate on what's called the K mechanism or the kappa mechanism. And this is from Wiki. So it says the cycle is driven by the fact doubly ionized helium, the form adopted at high temperatures, is more opaque than singularly ionized helium. Normally, when you compress a gas in a star, it becomes ionized, and that ionization allows photons a freer transport out of the star. They're not blocked by any electrons capturing them and re-radiating them in different directions. So the doubly ionized helium actually gets more opaque, less transparent as it's compressed. That actually causes the helium to absorb energy, gets warm, right? If you're not letting photons through and you're absorbing them, you're absorbing energy. So where does that take us? So you have a star and its doubly ionized helium is compressing, becomes opaque, dims the star, the gas warms up, expands, becomes less opaque, more transparent, lets more light through, cools off, and then pulses again. So in a normal star, it doesn't pulse. It'll compress till a certain transparency is achieved, and that's the light that shines through the atmosphere, the gases. All right. So now we have a distance marker that we can use by measuring a period. By measuring a period, and then measuring a distance. So you get the apparent brightness, and then you get the absolute brightness. And I think the absolute brightness, its intrinsic brightness, is how bright the object would be if it was 10 parsecs from Earth. Okay? This eventually leads Edmund Halley. So this eventually led to not Halley, he's the comet guy, Edwin Hubble. Okay? So Edwin Hubble in 1929 discovered the distance to the Andromeda Nebula by finding a Cepheid variable, measured its period, and determined its distance. And the distance he got was on the order of 2 million light years. This object was definitely outside the bounds of the known galaxy at the time. So now we have a distance marker, and using these Cepheid variables, Hubble, with Hubble's law, was able to find a relationship between the distance of a stellar object and its redshift. Hubble's law, you probably know it as Hubble's constant. And now we have a way of measuring distances all the way out to the far reaches of the galaxy. In the next segment, we'll talk about type 1a supernovas and the mechanism at which they became the next standard candle, and the ramifications of the comparison between the Hubble constant and the type 1a supernova data in the next part.